All right, today let's look at how to do a Birdstrike analysis inside LS-Dyna with SALE. So SALE is basically, this is actually one of the SPH run I did with Birdstrike. You can sort of see compared to the SALE, they look relatively similar. The difference between the two is that SALE is actually multi-material group. Uses a multi-material group to sort of model the fluid interactions with the structure, whereas SPH are using essentially particles, right? So I did a SLE model for a sloshing problem last time. So basically, in this case, the only thing that's really different is that I'm going to actually move the entire background grid, as you can see in this video here, right? So the reason that the fluid, the water can interact with the blade is because I'm actually moving the entire background mesh, and I'm actually stretching the background mesh to match what's happening with the fluid structure, because the fluid is actually moving upwards due to the movement of the turbine blade, and that's why the ALE domain is actually stretching in this case. So this is the overall workflow that I created last time. So what changed in this time is that I'm actually adding a few components, right? One is that we actually can use ALE structured FSI to define the fluid structure interaction. And also what we're going to do is that we're going to use a ALE structure mesh motion to define the stretching of the background grid. And lastly, we're going to use the initial velocity generation with a set node general to move the background grid. And that's really the major difference, right? So as you can see, oh, this is actually just where you generate the initial volume fraction, which actually didn't change this time. And then what we're doing here is that we're actually just adding a ALE structure mesh motion to the model, and we're adding a set node general to the model to move that initial background grid. Okay, that's really the difference. Everything else stay the same. We're still doing the same multi-material group. We're still doing the same ALE structure mesh, and we're still filling the initial volume here. But what we're doing differently is basically with these. And I'll explain these key cards in a bit, right? Now, let's go ahead and do a demo model together. Really, is the whole purpose of doing the video, right? Is that I have a dummy model that I've created, and I want to basically demonstrate how the model itself works. Okay. All right. So this is a very similar to the SPH model that I did. I'm gonna assign all of this to a material called blade, and the material blade is basically just a matte elastic with a matte air erosion. I'm sorry, a matte 24 with a matte air erosion added. All this right here is very similar to an old model that I created, so nothing fancy there. In terms of the actual thickness of the blade, it's going to be 20 millimeters, or 2 to the -3, which is the actual shell thickness on all of these bodies right here. Now for the background mesh, we're going to change this from a Lagrangian frame to an SLE domain, and then and then I'm going to add a material here. Now the material here is relatively basic. So all I'm going to do is that I'm going to use a matte node with a EOS linear polynomial to basically define the background mesh. It's basically essentially a node material. There's a little bit of a E0, which is sort of define the initial energy, or the initial sort of like the pressure gradient that's going to be inside here. Inside the background mesh. And then for the actual component, which is the bird itself, which is this component that's hidden inside here, I'm going to assign it to the same material I assigned last time, which is the bird material. Now if you look at the bird material, it's basically just a matte node with an EOS Gernison. This essentially represents water, right? This is exactly the same material I assigned with the SPH version of the model, except in this case I'm assigning it to here. And of course, I'm going to change the frame reference from Lagrangian to SLE fill. Right? That basically creates my combination of my background mesh with SLE domain and my SLE fill, which is going to fill with water. Okay. Now, once we have something like this, the next step we want to do is that we can go ahead and mesh everything. So let's go ahead and just do that. The mesh that we created is very simple. I'm just going to define I think the size I'm going to do here is I think something like 2 to the -2 meter, so it's about 20 millimeters, right? And if I were to match this, it would just give me a 20 millimeter uniform mesh across the board. And I'm not even defining like the section and everything. Most of this is relatively simple. The section card for the ALE material is going to be automatically defined inside inside the when we write out the input file. So everything else is basically standard, right? And then what we're gonna do next is that let's go ahead and add an SLE mesh right here. And then what we're gonna do here is let's go ahead and assign this body to the SLE mesh. And then what I would do here is that I'll go ahead and assign a 0.02 mesh across the board. You see that? Um, no, maybe we can even make it a little bit denser. Let's make that 0.01 across the board. Does look a little bit denser. Now, what's gonna happen here is that if you remember from my previous video about the sloshing, is that this background mesh right here is going to essentially form the ALE structure mesh, which is gonna fill the volume inside what we're seeing here, inside this highlighted green region. Everything inside that green region is gonna be filled with the SLE mesh, and it's gonna fill with that material that we define, which is this material over here, right? And that's really how SLE works. What we're gonna do next, right, is let's go ahead and define a. I'm actually going to. I actually have a name selection, I believe. Or actually, I don't. Let's hide this part. And what I'm gonna do here is that I'm going to actually select this whole thing, and I'm gonna call this blaze set. And this blaze set is basically a name selection that's gonna be scoped to the entire body interaction here, because I'm actually going to be very generous here. I'm just going to say, hey, this whole area, what I wanted to do. Oh, actually, did I miss a blade? Yes, I did. That's weird. I missed a blade. I'm going to add this blade here, and that's going to actually that's actually going to 1 second. I'm gonna turn on something. That's actually going to sorry about that. All right, sorry about that. Okay, so let's go. That's actually going to be assigned to this body interaction, and that's actually create a single surface body group, a contact group, which is gonna basically allow when the blade itself breaks apart, it's gonna allow them to see each other as a contact pair, basically. And the next thing we want to do is basically define a coupling, and the coupling is going to be between the Lagrangian body, which is the blaze set, and the Eulerian body, which is going to be our water piece. And I'm gonna set this to 4, and then that's basically defines my coupling piece, right? This coupling piece right here is needed because that's where we're going to define the contact between the SLE body and here. Now, so if you open up this thing and look at it, right, there are usually 2 different ways to define the coupling, right? One is with a constrained Lagrangian solid. One is with ALE structure FSI. In this case, we're going to define it as ALE structure FSI. Instead of using the Lagrangian solid, which is what I used last time for the sloshing problem, I'm actually going to use ALE structure FSI. This is just a simpler version of that problem. It's more suited for flow structure interactions. And then just to try it out, right, we're gonna basically use this, and that's the coupling method that we're using, right? And then once we do this, basically we have our Lagrangian body defined. Then we have our SLE body defined. We have the contact between them defined. We also have the contact between the blades defined. And that basically sets up the full model in a sense, right? Because the full model really doesn't contain anything else. That's pretty much it. But there's a couple little tricks that we wanna do next, right? So what we wanna do first, what we wanna do next is looking at the inside of this turbine blade. I'm actually gonna assign a remote displacement to it. Now this remote displacement is going to basically locate it somewhere in the center, as you can see right there, right? And then what I want to do here is that I want to change this to rigid, and then what I want to do is to make sure this thing can only rotate in the z-axis, which means it's free in the z-axis, and then not anywhere else. Everywhere else is going to be constrained. This is the first thing we want to do. The second thing we want to do, right, is to assign a rotational velocity, and that's going to be inertial rotational velocity to the backside, which is the same 13 faces that we're putting here. Oh, sorry. Well, I guess I can just assign it to the entire blaze set in this case. Yeah, so I just go ahead and assign to the entire blaze set. When this entire blaze set is assigned a rotational velocity and it's going to be assigned relative to the global coordinate system, along the z, and then the value we want to use is negative 225 radian per second. Is the value I use, which is going to basically spin this thing this way. Okay. Interesting. It's actually a little bit off from what I was looking at. Interestingly enough. Yeah, that's actually right. Okay, that's good. And then what we want to do now also is to add an angular velocity and then also assign it to the blade set. And in this case, same thing. We're going to add a 225 RPM to the initial velocity of this thing. Okay, so this thing is gonna rotate at 225 RPM or 225 radian per second with an initial angular velocity, and then it's gonna have a inertial load of the rotational velocity here. And this rotational velocity is the inertial load, which adds in some initial stress. And then to impose that, we're gonna add a dynamic relaxation with some general preload added to it. 1 second, add general preload, and then we're gonna assign the rotational velocity to it. And this is what this is gonna do is gonna turn on dynamic relaxations, and it's going to add the rotational velocity as a inertial load during the dynamic relaxation, which is gonna pre-stress the blade. And afterwards, this thing is gonna be spinning at 225 RPM, which is going to essentially continue that rotation speed. The termination time for something like this, we're gonna put this at 0.025 second, relatively short duration, right? And then this basically defines how the blade itself is going to basically be moved, right? And we're gonna add a few control cards. Let's add a default control cards. Now I'm not going into detail of exactly what I did with the default cards. I mean I've done a lot of these in the past. So if you're interested, you check out the other videos, right? But basically the default control cards give me the basic control cards that I wanted to use. The most important one is the control ALE that were added here. And then the default database card. Oh, sorry, this is actually a default control card. This is a default control card. This is a default database card. And the default database card, we're basically using the standard database card that we're using with the D3 plot being pretty small, giving us a lot of data to look at. And the last thing that we need to do, which is essentially assigning the initial velocity. Okay. Now, doing the initial velocity is slightly tricky here. First of all, what we need to do is to define a set node general. Uh, 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 so here is what we're gonna do. All right, I'm gonna copy what I have from my other template file, and I want to explain a little bit what I did here. Okay. Now the set node general, you see this card right here, which I'm gonna actually go to the presentations for a second. All right. So I actually talk about the ALE structure FSI here. Basically, the ALE structure FSI is gonna look at the mesh ID, which is the mesh ID of the actual ALE structure mesh. And that's this one right here gets it's going to be what's used. Uh, uh, I'm sorry, the DP IDs we're gonna be using ALE structure mesh, and that's why the ID there is 17. The 102 right here is essentially a part ID, which is sorry, a set ID, and this set ID is going to basically represent the Lagrangian bodies, right? And this -4 right here represents the multi-material group, which is going to be coupling with, right? So we need to call out the background grid. We also need to call out the ALE multi-material group, which has a set ID of 4, which is why it's a -4 here. And this is what allows the structure, which is 17, to see. I'm sorry, which is what allow the 102 to see basically the negative 4, which is the ALE multi-material group. This 4 essentially represents this body that we've added in the model, right? Which is this little green body, which has essentially ALE set multi-material group of number of 4, and that's what's happening actually in the background when we set a coupling object here. What's going to be written out is the ALE structure FSI. That's the first thing to know. Okay. Now the second thing to know is what I also wanted to talk about was that the set node general right here, right? You see it has an ID of 202, which is used in initial velocity. So you know initial velocity is basically going to drive this set with a 100 sort of meter per second velocity, right, in the z-axis. Which if you look at the model, that's essentially in the direction against the blade in the z-axis. Okay. Now the way this set node general works is that the SALE CPT option turns on basically allows the keycard to point out to the definition of an SALE body, right? Which is essentially actually is the background grid that we're essentially moving with the set node general. Now in this case, the E1 is referring to the mesh ID, which is the mesh ID of the ALE structure mesh. The E2 to E7 correspond to the control points, right? So you see 133, 151, 148 corresponds to the control points that generated the ALE structure mesh. This mesh ID goes into E1, and together the set node general is what the inertial velocity card needs to apply the inertial velocity, right? So if you want to apply inertial velocity to the entire background mesh, you have to use the set node general with a SLE option here, and then assign the mesh ID to here, and then assign the control points to the other 6 parameters. And that's really what's happening here is that what we did here in this area is that I assign my initial velocity, assign it to node to set 202. Set 202 defines the LC option, with one being the mesh ID of the SLE structure mesh, and these are the actual control points that's written out as part of this object right here. Even though this object here has 0.01 meter, the control points give you the number of divisions you need across that space, and that's really what we're looking for in these two cards. Okay. Now once we have this, the ARE structure mesh motion is going to basically call on the set 22 here, and call on mesh ID 1 to stretch that mesh by this parameter value here. This exp explem right here is basically how much is allowed to stretch, right? So this right here is basically allowing it to stretch by a factor of 2. So if you want the background mesh to stretch because of the movement of the fluids inside it, we can stretch the background mesh with the ALE structure mesh, and all you need is define the mesh ID here and the set ID here. Set ID here defines the background mesh ID in the multi-material group, and this mesh ID right here is the ALE structure mesh, right? So one is the background mesh, one is the air that's filling that background mesh up, and together they define how much it's going to be moving basically. Okay, these are all pretty precisely defined definition of how these work. So if you look at, say for example, the manual, I can show that real quick. It's worth taking a look at it real quick, right? So if you look at the ALE structured mesh motion, right? If you look at this card, right? So we have to pay really good attention. This is the mesh ID of the ALE structure mesh. This right here is the group list ID of the mesh that follows, right? So this is the actual set of the multi-material group, which is why in the key card I defined a new set of a multi-material group set and assign the first body to it. The first body is the first body in my ALE structure mesh, right? So if you look at my ALE multi-material group, right, you see that this right here is my first one, this right here is my second one, because they're always referencing order, right? So I don't actually have a set 22 here, which is what I define here. The first one is always going to be my background mesh, which is hidden, right? This right here is going to be my number one, and that's what's referenced in this set multi-material group right here. And that's what's also referenced inside ALE structure mesh motion, right? One is the ALE structure mesh ID, the other is the set ID for the first body that fills with air. And we're basically just following the GC of that huge body, of that square body, and allow it to stretch by a factor of 2. And that's what you're seeing in the presentation here, is that it's able to actually stretch out because of that behavior that you're seeing here, like that. Okay, and the reason this is necessary because you can imagine the fluid body basically expands as soon as it hits the turbine blade. That's why we need to capture the stretching of that mesh body, of the background mesh, to allow us to capture how much the fluid is moving. I actually didn't stretch it enough. You can see it sort of disappears as soon as it hits right here. When in reality it should be much bigger of a background mesh, to fully capture the sort of the interactions as the water particle sort of separates, right? And this is where it's sort of not really matching the SPH. SPH doesn't have a background mesh, so you have this boom effect where the whole particle just goes everywhere, right? This thing isn't happening here is because our background mesh is too small to capture all of that. But the basic technique is here, and that overall is how you set up a SALE Birdstrike analysis. And in post processing, you can sort of see I have my ALE group right here, right? I can disable it, and this is my original body. Remember, these two bodies are actually not used bodies, right? These are just Lagrangian body that's like a spacer. They define the region for the inertial volume fractions. The ALE bodies was actually happening here, and then when I run this, you can sort of see this is where interaction occur with the turbine blade. The background mesh passes through it, but we're applying the initial velocity to the background mesh, allowing it to stretch to cover the behavior of the fluids. And that's the beauty of a SALE model, right? You can sort of model this kind of interactions in for a variety of different problems. And I'm gonna keep doing other problem like blast, like explosion. There are other cool things that we can do. It's a very useful technique to capture that kind of physical phenomenon, right? Where we want to model a fluid structure interaction, but without having to do a complex CFD analysis. We can sort of model the fluid behavior as a bulk response inside the Lagrangian frame, and it becomes a very useful thing to do using a sort of a mixed formulation like a Lorentzian and a Lagrangian element like SLE that we're doing this with. Okay, I hope this helps. Thank you very much.